Popat got his master from Massachusetts Institute, MIT, and also his PhD from there. And he's currently a research scientist at Google. And prior to that, he actually spent quite some time here in the Valley. He worked at Xerox PARC. And somewhere in the past, he was also visiting research at my alma mater in Switzerland. So with here, I give you the speaker. Thank you very much.
So thank you all for coming. Thank you, Radha and Yele and John and Pavel. And it's a pleasure to be here. So I'm going to talk about optical character recognition. And first, a brief introduction to it. Then I'll tell you in relatively high-level terms what we do in our system at Google. And then I'll just take the liberty of making some reflections and comments. And I don't claim to know any truths, but I thought some of it might be interesting. And then, of course, I can also learn from your own comments. So what do we mean by optical character recognition? So these are all meant to be examples of different instances of OCR, different flavors of it. So here we have this very clearly machine printed example of text, a text line taken from a printed book, all capital letters. We have handwriting input here. In this case, it's device input where you have the time trajectories with a stylus. So that, the application here might be digital input. Many of us still have, in our daily lives, we still make whiteboard drawings, or maybe we have handwritten notes of different types. And it might be interesting in some cases to be able to index those for later reference. So that's another instance of recognition, text recognition. In some specialized applications, we may have some quasi-linguistic material. So this is a two-dimensional representation of chemical formulas. Music is also, let's say, quasi-linguistic. You can imagine designing some sort of grammar to parse it and to extract some structured meaning within the domain from these representations. And the same goes with math, right? So you can imagine maybe a two-dimensional grammar, maybe even context-free in the case of math. So these are all related to, when we say optical character recognition, we might include all of these, but I'm going to talk about what we do in a narrow sense. Let me just say that I'm involved with efforts in Google to work on this one and the top one. Let's see if I have an animation. Yeah, so these two. But then also increasingly this kind of stuff is becoming of interest also to what we're doing. So that gives you some context. Why is Google interested in any of this? Well, we're very interested in making information available and useful to people and organizing it and helping people, letting people find it. And increasingly that's not just in the cloud, but in their lives, right? So that's something that is important to Google, and a lot of the information is in physically printed form. And even if it's not physically printed, it's for human consumption, which means that an interface that's always going to be respected and present is the optical interface to human beings. So even on screens or displayed signs in train stations, whatever, even though it may start out digitally, maybe it's available to us in kind of a visual way. And wouldn't it be nice and interesting to be able to deal with it digitally? So imagine your mobile device pulling it out, and maybe how many people here have seen WordLens or used WordLens or heard of WordLens? So for those of you who haven't, it's a product that, Google now acquired WordLens. It's a product that allows you to take your smartphone and hold it up in front of some printed text in one language and then visualize it in your own language in kind of real time. And they even, it even renders like the original in the original style and colors. It's pretty cool. So that's all of that stuff is within scope of what Google can and arguably should be interested in. So that's a little bit more context. Let's see what I have next. Okay, so let's take this first example. Is recognizing the so when we say OCR, we mean converting this text to, let's say, in this case, ASCII, right? Just recognizing each character. Is this a difficult problem in this particular example? Probably we'd say no. In the grand scheme of things, it shouldn't be that hard. You could imagine a semester or undergraduate class, somebody doing a final project that gets 100% accuracy. That, I'd give them, they wouldn't even necessarily get an A for getting 100% accuracy, right? It's not that hard, right? Okay, well, one minor point is that we have big capital letters and little capital letters. So there's a slight nitpick that maybe the little capital letters are small caps, which are semantically lowercase. And maybe we want to be able to figure that out. But even that's not hard, right? So maybe you do give them the A if they get that part right, and they get a B if they just get all caps or something. I don't know. We can have different typefaces. In both these examples, how would we do this? How would we solve this problem? But by the way, is there anybody here who has worked on optical character recognition? Very cool. Brothers. All right. So how might we do this? If this was the total scope of what we cared about, this sort of problem, these sorts of instances, what might we do? Well, I can tell you what I might do. Especially if I were working in 1975 or 1983 and I was worried about memory and other things, I might first binarize and then maybe encode the contours or something, do chain coding, have the whole page fit in memory. That would be exciting. I'd separate the characters out. I'd try to recognize each shape independently, maybe. To handle the second case, I might use clever moments of spatial moments, geometric moments, maybe topological features, right? And that would get me pretty far. In fact, that's what people used to do. Handling again with the slant. That also, if we define slant invariant features, then we might be able to identify features that allow good discrimination among the 100 or so character classes that we care about. So it's not rocket science yet, right? Maybe it's never rocket science. I'm not claiming that OCR is rocket science, by the way. Okay, now this is a little bit more interesting. So, we have some distortion to the image, right? Some of it's a little bit lighter. Maybe some of the strokes are a little bit light, hard to see. So, traditional Chinese has an interesting, rich history. It evolved from systems where the radicals were more easily identified. It's still a representation of spoken utterance. So all of the extant writing systems have this in common. I mean, we think of Chinese as maybe being a little bit logographic, but in reality, it is representing the spoken utterance, and all modern writing systems have that in common, that you're trying to reproduce a phonological sequence.
Excuse me, I thought the same Chinese is read phonologically wildly differently by many different dialects and languages.
Yep.
So your statement's slightly puzzles.
I'm not claiming it's the same phonological sequence, but the purpose is to represent, if I'm not I could be wrong, but my understanding is that the purpose is to represent a phonological sequence. So are you saying like between Mandarin and Cantonese it might be very different? Even if one can read the other, then it's a different. I'm not claiming that it's the same.
There are overlaps between the Chinese dialects and Japanese, which have the same character, but the spoken languages they're wildly different.
So I'm not claiming that the languages are the same. I'm claiming that within a language, the purpose of the writing is to represent the spoken utterance. And the reason I make that point is because that's powerful, right? Because what that says is that maybe text recognition, at least text lines, right? I mean, there are issues about layout and presentation and typography, but maybe the fundamental problem of recognizing a text line, maybe we can look to natural language processing, what's done in speech recognition, sequence labeling. Maybe we can look at techniques that are successful in other natural language tasks to be useful in optical character recognition. I'm not saying that we have, for the first example, you know, if the person doing that semester project decided to go out and write a dependency parser or do some other deep natural language processing with conditional random fields or whatever, they're not going to finish their project, right? It's not that hard a problem. But what I'm trying to do is set up a progression of ideas that will suggest that we might want to be considering something beyond that semester project. So here, another example, another reason for bringing this up is because in the previous cases, we're talking about an effective alphabet size of maybe a few hundred different distinct symbols that we have to distinguish. But now in the case of traditional Chinese, at least 5,000 for something respectable. If we wanted to handle, old philosophical treatises, we might, need more, 10,000, even, 30,000 or more. Are there any native Chinese speakers or even better Chinese scholars? Would you like to comment?
100,000.
100,000.
Yeah.
Okay. So, now it starts to become interesting, right? 100,000 characters. So, and as you said, the kanji in Japanese is from Chinese. Officially it's roughly 2,000 or so characters, but of course with place names and proper names and other things, then it's going to expand very quickly. So you don't get a free pass just because Japanese officially decided to restrict the kanji part to a few thousand. Okay, here's another example of something interesting. So our system has to be able to recognize this kind of stuff, right? And so now all of a sudden your semester project got really hard. And we start to read this, and then all of a sudden we get some Latin, and so now we have to go here and read that. Or maybe we go here up to there. Anyway, maybe that's a left parentheses, maybe it's a right parentheses. It doesn't really matter. It looks the same, right? If it's part of the Arabic, then it's an opening parentheses, right? But you could also imagine it's part of the closing parentheses, as part of the Latin. Anyway, you have some convention, you figure that out. So you read this, and then you go this way, maybe, and then you continue this way. And you're going to have to, if you're going to separate this stuff into characters and then do your shape recognizer, then you have to be aware that the presentation forms for Arabic are going to differ depending on what part of the writing you're in. If you're at the beginning and the end, if you're isolated, if you're in the middle of something, these all can be different, right? They all look different. Okay, and here's a nice example. You can get inputs that if my first step is to binarize or to separate into different character glyphs, then this might be a challenge. It's halftone, right? So let me just summarize the simple approach, which is what was done for years, and it was probably the right thing to do because the commercially important applications of OCR were like office documents in the Western world, French and English and German, and the Japanese also were interested in OCR in the early days, and a lot of the progress was made by the Japanese researchers. But the kind of vanilla processing that you would do is you'd binarize the image, you'd try to identify these features, and you'd classify, right? Lots of different ways to classify. Okay, let's look at, so my motivation for getting into this at Google initially was I worked both on the Books project and also on the Translate project, Google Translate. And we were interested in hypothetically seeing if the books could be a source of interesting parallel data for training a translation engine. for learning the phrase table in a statistical phrase-based translation system. And you know, at the end, this was just a plausibility or feasibility study. In the end, we'd have to get okay from whatever legal counsel to actually go ahead and do this. But one thing we noticed that when we couldn't even get started because our OCR was so bad for any of the obscure languages that we were weak in the translate system. Right, so our translate was weak in Khmer and Burmese and these other languages for which we had trouble getting data. So, you know, there were some books in those languages, but we didn't have any OCR for any of that. So that was interesting, right? We could maybe we could try to improve the OCR. So that's how I got into this. Oh, I wanted to actually say something about this. So this is also an interesting example because in many systems, if you actually use an off-the-shelf commercial OCR system, it may not let you say that the left-hand side is ancient Greek and the right-hand side is Latin. Load the language models appropriate for whatever's on the page. It may not let you do that. But in reality, you often want to be able to say, I don't care what language it's in, just go recognize it and give me Unicode. Like, why are you asking me? You know, the OCR should be able to figure that out. Right? So we wanted to get to that state where it could easily handle the two columns in different languages. And then even within a paragraph, so you can have script and language variation within a paragraph. Right? Can anybody read all of this, by the way? Raise your hand. Very impressive. Very good. So what are the different scripts there?
It looks like Russian and Slavic and German.
Pretty cool.
Oh, German.
I notice there's a long S here, which means it must be old. Okay, here's one which I'm going to ask the same question. Now, whoever gets this, I will sit down and then you can give the talk because you know more about this stuff than I do. Anybody recognize everything here?
Some of it.
It looks like a little bit of German with Sanskrit.
Some Hindi, Sanskrit.
Yeah. And then we have some transliteration also, probably, right, into Latin. So the reason I have this here is because internally we've had discussions about whether it's really important to be able to handle mixtures of scripts. And one idea that came up was maybe we don't have to handle all combinations, right? Maybe it's sufficient to say that anything, that English can happen with anything. Maybe we'll make a special allowance and say that French can happen with Arabic. And, you know, try to do the pairwise possibilities, or triple-wise maybe possibilities. But, you know, we do find stuff like this, and why not? Let's do it. We're Google. We care about the world's information. We shouldn't play favorites. Let's recognize everything. So that's the motivation here. And the challenge. Okay, so we're talking about optical character recognition, but we haven't yet said what a character is. So if you're in English, a character is pretty simple. It's ASCII, right? We all know that A is 65, right? So we know what a character is in English. In other languages, it's not quite as crisp. There's a notion of grapheme cluster, which roughly means what is perceived by a native literate person in the language as being a character unit that they would like to treat as a character for the purpose of, let's say, text editing. When they hit backspace, how much do you go back? Right? Well, hitting backspace should go back one character. In the case of Devanagari here, I'm actually not a native speaker of Hindi, so my colleague Dimitri is actually the expert on Hindi, and this is his slide. But I think the main point of this slide is that if you have a Unicode sequence which grows in this way, then the rendered glyph sequence, or the character, grows in this way. And if there are any native Hindi speakers or people who know Devanagari, you can confirm or correct correct me on that point. But the point is that, you know, all of these, I think all of these are considered maybe single characters for the purpose of, you know, the semantic notion of what unit is a character for a grapheme cluster, right? So even in a language like Hindi, which we think of as not having as many characters, let's say, as Chinese, depending on how you do your OCR or how you define characters, right? We actually want to do recognition on the stuff that we can isolate, right? Even if we have some provision for treating it as a connected sequence like in Arabic, still the things that are connected you want to be able to deal with reasonably, right? So in Hindi, one way to approach it is to say that we have also thousands of characters, and that's also true for, you know, virtually any of the Southeast Asian languages except for Vietnamese. In fact, it's even more complicated for these other, for some of these other Asian languages. And I mentioned there's bidirectional issues. I won't say more about this, but you start with the Hebrew and then you get some English and then go back to the Hebrew. I think we've been over that. And then connected scripts, and not only connected scripts, but you have, you know, different styles. So in some languages that are written with Arabic script but are not Arabic, so for example, Urdu, Persian, Farsi, Pashto, they're written with Arabic. They tend to have this Nastaliq style, and the Nask style is more common in actual Arabic. So going back to our semester project, our undergraduate semester project, let's say you wanted to include Arabic. What do you do? Any ideas? Neural networks. Okay. I think that you don't get credit for that because that's the answer to every question. So. In fact, you can even say what kind of neural network. You can say LSTMs. LSTMs are the answer to everything. I'm half joking. Yeah, so basically you want to come up with something that doesn't necessarily try in advance to break up the problem into pieces that have individual answers that you later piece together. You want to consider things a little bit more holistically. Right? Okay, so now I'm going to tell you what we do, but I'm going to tell you what we do at a very high level. And I was telling David earlier, the reason for that is in part because I'm piecing together parts of previously cleared slide decks, and I pieced it together relatively late, as the organizers can attest, and as a result I wasn't able to get sufficient lead time to get clearance to tell you many details. So that's one answer for why I'm not going to tell you a whole lot of deep details, but another answer is because they're not important, and I'll try to make that point later, that it's really not the actual details, the topologies of the different neural nets involved, and you know, our graph search algorithms and pruning algorithms and all that. It's not that important, and I'll tell you why later. I claim it's not that important. Okay, so we're going to narrow the definition of OCR just a little bit more. So here we start out with some input document. It's a page of a book. Then there's pre-processing and layout analysis that happens. So the pre-processing might be to fix any tilt or slant that might be in the page. Maybe if you're taking it with a camera, then there's some warping. It has to be de-warped. And then you have to find out where the text is and where the line drawings are and where the halftone images are, other graphics. You want to separate that out so that you treat each part appropriately for what it is. Maybe you want to know where paragraph boundaries are. Maybe you want to know that something is likely to be a title because of its position and its size, so that you can treat that differently for the purposes of indexing. For example, you might want to give titles special status in indexing or retrieval. Anyway, so you find out where the text is, and then we pick out a line of text, and we cleaned it up a lot, right? So we made it not be curvy anymore. This is a particularly clean image, but maybe we had a noisy image to start out with, right? Now, this pre-processing and layout analysis, I'm showing it in kind of a pipeline fashion, but maybe one could do a better job in that step if you fed back some of the semantics that you get out of understanding what's on the page. Right? So the way I'm showing it, we're not doing that. Okay, we're assuming a pipelined architecture, and that may be limiting. Here's text line recognition in the narrower sense that I'm most concerned with it at this stage. And the primary output or the primary task is to render the Unicode sequence that corresponds to what's written. And to make that more precise, we would like to obtain a transcription that would be the same as what a skilled, literate person, native and knowledgeable in that language, would type in. And so one question is that uniquely defined? Is there a right answer? You know, do you define it ideally in terms of the author's intent? What if there's a spelling mistake in the actual printed text? Do you want that corrected? What if there's a long S like we saw before? Do we want that turned into a modern S so that people don't think to themselves the letter F, the F sound instead of the S sound, because to our eyes we don't read long S's that well? These are all interesting questions, and I actually did some experiments with human raters to see what the error rates are for transcribing the inter-transcriber agreement, right? So a human sees this line, another person sees the same line, and they type something in, and you do that for many lines. How often do people agree? And you know, obviously, they might disagree on, you know, is it an M dash versus an N dash? Is it a, I don't know, is it a Chinese space character, or is it regular ASCII 32 space, or, you know, that sort of thing. So we make allowances for that. We can normalize that out. But it's surprising what people will do sometimes. They will actually, often they will correct errors that were there in the original text, because they, you know, the human perception and cognition is such that, you know, we don't necessarily see things as they are. Okay, let me pause there. I generally would prefer questions in the end, but it's okay to interrupt me, especially when I say let me pause here, because I think this is a good pausing point. Yeah.
So I understand that you might potentially want to leverage on the context of a paragraph to determine what character it is.
Yep.
But have you ever had the need to actually look inside the character in the sense that, because even whether it's a Chinese character or even English characters, Latin characters, they are essentially composed of individual strokes and dots and so on. Have you ever needed to look into that, decomposing into that level?
Yeah, so we have, and we do. And the way we do it is actually, rather than using the character, especially, you know, having said what we said earlier about how the definition of character isn't necessarily crisp, we've defined fundamental units of recognition. Where we do our graph search, our elementary hypotheses are in terms of what we call atoms, which are subcharacter units. And the way we define subcharacter units actually is one of the few language-dependent aspects of our system. That's a great question, thank you.
Question, another one. Apparently you have looked 8 or 10 languages here. Can you put little bit hierarchy, which is the easiest in OCR and which is the most difficult in these 10 which you described?
Yeah, let me see if maybe my colleague Dianish might be able to help me out on this one, but off the top of my head, the problem, okay, here's one problem in answering this question. Mm-hmm. If we're looking at character error rates, then each Chinese character, for example, is worth a few English characters, right? In the sense that Chinese word might consist of, 1 or 2 characters or something, whereas an English word might consist of, between 5 and 7 characters on average. Another way to think about it is, let's say we're looking at the information rate, the per character information rate of English. So, depending on the domain, it might be between 2 bits per symbol and 2.5 bits per symbol on average for large corpus. In Chinese, for traditional Chinese, it might be 7.5 bits per symbol. So I haven't gone through the exercise of trying to propose an interesting metric that would normalize across languages to give a really quantitative, empirical answer to your question. So I think in terms of difficulty, I think there are different sorts of difficulties. I think in terms of our state of the art, probably still CJ is relatively hard, and for some reason K also seems to be hard. Chinese, Korean, and Japanese. Southeast Asian, although I would have expected them to be hard, Thai and others, I think we do pretty well. And our internal benchmarks, I'm not going to have any actual evaluation comparisons in terms of accuracy here, because for the reason I mentioned earlier, right, it hasn't yet been cleared for external dissemination what those actual numbers are. But my experience roughly has been that we're better than commercial engines on most languages, and we're surprisingly better on certain languages that are hard, and we're not as much better as I would have hoped on languages that are medium hard. So I think we blow people out of the water in certain languages. Maybe that's not the right expression. We do really well on some languages, including some that I would have predicted are very hard, like Southeast Asian scripts. Yeah.
How do you extract the line text or line information in a stage one? How do you do that?
We're not doing anything novel there. We're reusing tried and true existing methods that were developed years ago. There are 2 basic approaches. One is top-down and the other is bottom-up for finding texts, text lines, words, paragraphs. I actually don't know. We're using internally a library routine that somebody else wrote within Google.
Internal library to do it.
Yeah.
Software.
If I understand your question, you're asking how, in detail, technically, how is the line extraction done from this page? Is that?
Right.
Yeah, my answer is that I don't know, and I find it an interesting question, but my focus within the scope of my project has been to realize that there may be something interesting to do there. In fact, we know it because a lot of our errors are actually due to bad line finding.
Right.
But I don't have the expertise in that. I don't know what.
So who did it?
Oh, somebody else at Google?
Outside Google? Or
No, in Google.
Inside?
Yeah. Inside Google. Yeah. Sorry?
Different group do it, not in your group.
Somebody else in Google, not in my group. Right. Yeah.
What file format do you use for the output of a page that looks like the top of that input document where you have a drawing with text?
Yep.
In Google Books?
So for everything we do on my team and most of what we do at Google, we're using, that I know about, so this is my opinion, we're using protocol buffers, which I don't know if you've heard about, but they're also open sourced to the rest of the world. So think of it as an alternative to XML that can have some efficiency advantages over XML. But it's an arbitrary way of, it's a way of serializing and communicating arbitrary structured data. So you have fields, and they're typed fields, and they can be serialized, and
output, is there a reader that takes that as input and produces a page that looks like the original but with the OCR done?
We have tools internally that will take, so this is a good question. So we do pre-processing and layout analysis, and one question is, well, what is the format of the data stored here?
I'm talking about the video.
Okay, yeah, and the same question applies at every arrow, right, in this diagram. And you want to have a representation that is convenient, that's serializable, that is portable, that allows, that's extensible. So you want to have a format that allows, like, for example, let's say I decide initially my pre-processing has rectangular bounding boxes as part of the information that's yielded from the layout analysis. And then later I decide, well, you know what, maybe I want to have parallelograms or polygons as my bounding boxes. Right? So you want to have a representation that allows you to make those changes without breaking all the data that you've already produced. Right? So these are great questions, and they're great software engineering questions. And our answer at Google so far seems to have been mostly protocol buffers. And if you have a web browser, you can type protobuf or protocol buffer, and you'll find the open source page for that.
So it's like PostScript, but not PostScript.
Well, I think of PostScript as being a page description. It's kind of a PostScript is interesting. In fact, I'll come back to PostScript. Yep. Yep.
Are there any plans or likelihood that this project will be open source?
I hope so.
For other app developers
or
potential apps?
You know, as somebody who's put my blood, sweat, and tears, and cries of mirth and joy into this, I would certainly love to see this open source. But I can't speak for Google. Maybe, but we have a product manager.
Yeah, that is certainly something that's on our roadmap. We aspire to get the OCR technology out into the hands of users, not just through Google products, but also for API and developers. And getting it open source is certainly a promising way for us to do that. So it's certainly on our roadmap to consider that. There may be other ways by which we can accomplish the same goal, but it's something that we'll have to decide on over time.
Okay, so within our project, I should say there are other OCR efforts at Google in various stages of where they are. When we started this particular project, we had some goals. So we wanted to be universal, so we wanted to handle every script and language that anybody might reasonably care about. Now, okay, that's not crisp, right? Because somebody might reasonably care about cuneiform. I don't claim that that's not reasonable, but we're not probably going to handle cuneiform. We also care about omni-setting. And what I mean by omni-setting is that, we think, at least those of us some people have worked in OCR for a while. The traditional scenario for OCR was you have a sheet fed or a flatbed scanner that gives you a very nice flat page and controlled lighting, very clean. And you're taking a picture of office documents. So these are dense text with very clearly delineated standard fonts typically. But increasingly, people want to be able to use their mobile phones. Maybe they don't have good lighting control. There's shading. Maybe the shadow of their phone or their hand is in the way to change the lighting. There might be curvature. Maybe there's some motion blur because it's hard to hold the camera still. Maybe you're taking pictures of, from a car. Maybe you won't care about street signs. Maybe there's occlusion. Maybe there's perspective distortion. So we're really interested ultimately in handling omni use cases, right, of OCR. Maybe we also care about doing it from video. That might be interesting. Okay, accuracy and speed. So we wanted best in the world approaching human accuracy, and internally our current evaluation metrics are showing that we're kind of on track for that. Initially we wanted speed to be comparable to commercial engines, and let's see if I don't animate my next bullet, which is actually in the last couple of years we found that was too conservative. We can actually go very fast and be very accurate, and that's thanks to a colleague, primarily the work of a colleague, Yasuhisa Fuji, who is just amazing. He came from a speech background. Okay, so now let me continue to tell you about about our approach. So our inspiration, and I just realized I'm moving a little bit slowly, so I'm going to speed up. Our inspiration was in Markov-based approaches that were developed in the 90s. So Gary Kopak hired me at Xerox PARC, and I worked with him and Phil Chow had previously worked on this project also, before he moved first to a startup and then to Microsoft. The other kind of major system that's worth mentioning probably from that era is the Bolt, Beranek, and Newman system based on their speech recognition engine. And they kind of had the first really successful Arabic OCR system. For some strange reason, DARPA was really interested in Arabic. Maybe they're all Sufis back there, just really interested in Arabic. Okay, well, let me just say about this. Why would we look to systems that are suitable for speech to handle OCR? Well, I think that there are probably many answers, but I think at a deep level, at least for me, it seems that it's going back to this idea that the writing systems of the world try to represent actual spoken utterances. And so that kind of inescapably, to me, leads to the notion that if you can find the right intermediate representations, the right feature sequences, then speech recognition might be a reasonable approach. I'm not claiming it's the right approach for the simplest cases that I showed initially, where you have well-separated Latin script characters. I think that's using too big a hammer. But I think if you want to have something that's general and that's going to pretty much work everywhere, then starting with looking at what the speech people do, that may be a pretty good start. Especially considering the great improvements speech recognition has made in the last decade or so. And oh, by the way, where does speech recognition come from? It comes from signal processing. So let's celebrate that. Sometimes it's forgotten. Some people tell me, speech is a great example of a victory for AI, right? But AI were those people typing lots of parentheses in list machines, and it was really the double E's and the signal processing people who made possible speech recognition. Okay, so what do? We basically do the same thing, but with a slight generalization. So I reused this from a previous audience. Everybody here knows this, so I'll go quickly. So this is kind of the noisy channel model. So you imagine that some source produced the actual message M that you're trying to recognize. And so our ideal message is a Unicode sequence. And the channel, which in this case consists of the cascade of typesetting and sitting on a library shelf for years and getting yellow, and then somebody spills coffee on it, whatever happens, and then you scan it in at some resolution, and maybe there's some distortion. So the channel renders some observed image X that has a conditional probability. This is the channel, the conditional model. And the OCR task is, given this observation X, which is the entire, in this case, the entire text line, with whatever distortions it contains, to produce an estimate of what the real message must have been that was produced by the message source. Okay? And one plausible objective would be to minimize the error rate. So choose that value of M as your estimate, which maximizes the posterior probability P of M given X. Right? And we know that will minimize the error rate at the line level. Okay, so that sounds good, right? I mean, who can argue with that? People do, but let's assume that it's reasonable. So here are two challenges. Nobody tells us what this probability is, right? So that's the modeling task. And the way people typically do it in speech is they take this likelihood and they take some prior, which is a language model, they multiply them together. They observe that they don't have to normalize that because you would divide that by the marginal for the observed image, but you don't have to since that's given. So it's irrelevant to the task of figuring out what the best M was. And so then that gives you the usual formulation in speech recognition, the starting point. But the modeling task is a little bit tricky, right? If you do what I just said, then you still have these questions. Well, what's the structure of the component models, right? And that's actually part art and part science, and I think data has a lot to do with it. But now, how do we compute this argmax, right? Even if we knew this a good probability model with the right parameters, how do we actually solve this decoding problem of figuring out the best M? And as you can imagine, it's so let's start with the component models. So I'll get back to the decoding. So our language models are character and word n-grams with appropriate smoothing. And the likelihood component, historically in speech, the idea was to have HMMs for the individual things you're trying to recognize and then to concatenate those together to get a search graph and then to find the best sequence of states and then to read off what characters those belong to. And within each state of the HMM, you have an emissions probability, that is a probability of what you observe when you're in that state. Right? And in order to model that, typically people have used Gaussian mixture models because they're kind of flexible and learnable, non-parametric, and very powerful, right? So you can, whatever your feature space is, you can reasonably fit a mixture of Gaussians. So document image decoding was interesting. I promised somebody I was going to come back to PostScript. So document image decoding was another mark of model-based approach to OCR, which Gary Kopek and Phil Chow pioneered. And it was incredibly accurate. It was like an order of magnitude less errors than commercial systems, with a caveat. The caveat is that the templates, the models, had to be really well matched to the sources. So if you were willing to put in the effort to learn models specific to a particular class of source, which often you were often willing to do that, then it was just very, very good. So what we do is we use a sliding window, a deep network, and HMM. So the deep network is our feature extraction. So in speech, people typically use some sort of spectral features, right? You have a 10 millisecond or a 20 millisecond window, and then you compute some spectral signature, Mel-Kepstrel coefficients, and look at the power or something like that, right? Phase isn't that important. But of course, for us, phase is important. And we don't necessarily look at spectral characteristics. We use just sliding windows of the pixels themselves, or we can use some sort of dimensionality reduction as a first step. But lately we've been just using deep networks, deep neural networks, to learn the features. And then we still retain the idea of using HMMs. Okay, this is probably my final slide with any detail on it. And that's good because it's getting late. Okay, so here's an observation. First of all, what's this? What is this silly alpha doing here? That wasn't there before. What's that all about? Anybody? Any speech recognition people here? Bayes' rule doesn't tell us there's an alpha there.
Redundancy?
So I think I actually don't know the answer. I was hoping, maybe it's redundancy. But what I'm told is that because of the way these different things are implemented, so this is typically in terms of continuous densities, right, Gaussians, right, so those are not probabilities, those are densities, right, whereas the language model is probability mass function, so it's really a probability mass function where this is something that needs to be normalized. It's, I don't know if that's part of the answer. Another part, well, I think they're different answers. Maybe the quality of the models are different. But anyway, it's long been known empirically that you find some fudge factor to exponentiate one of the two terms. You could either have alpha here, or you could have beta there. Doesn't matter. But one of them, you weight them relative to each other.
So PM is your prior, is it? Your language model.
That's right.
So you're okay.
Yeah, you just
so
give it a different.
Like a hack.
You give it a different way. It's a hack. It's a hack, right? We started with this beautiful phase, everything, right? Everything was beautiful until we put that alpha in
They
there.
just inverted the hack to make it look not like a hack, right? By putting it into the...
Right. Okay, so since we're doing hacks, and since hacks seem to work, why don't we go one step further, right? Here, arguably, we still have a posterior that we're trying to optimize. We have two terms. One is a language model. One is a likelihood. Let's throw in some more features in a log sum. Let's just have feature functions, and let's get some lambdas, and let's just it's just a direct generalization of this. Here we have two terms. Let's just have a bunch of terms. All right. So a former colleague at Google, he left Google, brilliant guy, he's still brilliant, he's doing brilliant things. Franz Auch actually headed the Translate project at Google for many years. And I became aware of this idea through him. And it's kind of an interesting idea because what it requires is that you give up the idea that you're being principled and computing in the end some well-defined posterior probability according to the established rules of the probability calculus. You just throw that out and you say, hey, let's try this, it might work. Right, so that's kind of it's a daring leap for some people. Anyway, we have a way of learning the lambdas, again, from Franz. It's called minimum error rate training, and it's used quite often in machine translation. Okay, so that's probably the last bit of math. And I won't pause for questions unless there's a really pressing question, because I realize I'm running out of time.
Can you answer one business type of question? Google doing Yahoo, Facebook, LinkedIn, they all will be doing OCR. Do you see some startup with new ventures funding to do the OCR startup?
Oh, that's interesting. I don't have any particular insight into that, but I think it's interesting. Okay, so our idea was to minimize language-specific engineering. We want to do we don't want to do pipeline stuff, despite what I told you earlier. Let's take advantage of data, and I'll maybe say a little bit more about that later. And let's also stand on the shoulders of giants. And I just mentioned machine translation, also speech, natural language processing, computer vision. They've all advanced, right? One thing I should say is that the bulk of investment in OCR research, I think, was done years ago, before many of these advances. And as a result, a lot of technology has matured, which for Western languages is perfectly respectable. We can even think that OCR is kind of a solved problem for English, in the sense that you can go to Fry's and get a little shrink wrap, package of Acrobat or something, and it'll do OCR for you, and they don't even charge for it. It's just expected, right? So OCR, in some sense, is considered a solved problem. There are a lot of sunk costs behind that, and so it may not make sense for these companies that have that technology or that have acquired that technology to maybe be investing in the research to make it work on Khmer, because they don't care about Khmer. They're not going to sell a lot of software in Cambodia. But we care because we're Google and we care about the world. I mean that. But the people I know in Google care about the world. Let me put it that way. Okay, here's a graph that I censored from my slide deck because it actually had graphs and numbers. But I think I will say that if you looked over the time span of our project and you plotted our accuracy and our speed, both have gotten dramatically better over time, thanks to our methodology and our use of data. Okay, and just where have we gone? We started with GMMs. We replaced them with deep neural networks for our feature learning. And then beyond that, also to directly estimate the state posteriors, right? And then deep neural networks are now, we're starting to look at long short-term memory neural networks, both bidirectional and unidirectional. These are recurrent neural networks. And different ways of training, sequential discriminative training, which is used in some speech systems. Instead of statistical engrams, we're looking at recurrent neural net language models now internally. And if you want to look at some details, look up my colleague Yasuhisa Fuji with 2 I's at the end, F-U-J-I-I. And I think he had a paper in this last ICDAR that just finished last week in France. Okay, so let me just say quickly about script and language identification. So remember those ancillary features that I said were desirable but not essential products of recognition, things like style and font, right? So if we're doing the recognition, then as a byproduct, we probably need to be learning those things, at least implicitly in our system, as some latent variables that get adapted over. Fortunately, those things tend to be spatially coherent, both because of typesetting conventions and probably because writing is intended for human consumers, and perceptually we need coherence. So, you know, figure captions will tend to be in one font, and then maybe titles will be in another font, but you won't get, it won't look like a ransom note where sizes and shapes are just varying continuously. There's some coherency. And so then they have those factors, like what language is it in, or what style is it in. Treat it as a sequence of labels or a sequence of states that has a lower rate of change, and the class of possible values is smaller than, let's say, the actual Unicode values. Right? So it's an easier problem. So why not use the same setup, and let's reuse our system that already is good for sequential labeling, but let's just retarget our same system to estimate some of these other characteristics. Namely, why not use it to estimate script? And so a couple of years ago, my colleague Dmitry Genzel looked into this and got great results, and we I think we have a paper, and it's here, actually. Here's a paper at the bottom. And the idea is just use an OCR engine to do the script identification as first pass, and then once you know the script, rerun the OCR engine knowing the script, and then you get great results without knowing the script in advance. And the price you pay is it takes a little longer to run. Okay, there's another approach that my colleague Yuanpeng Li and Daniel Holtman Rice have worked on, which is to use computer vision. And the idea here is very simple. If we look at these, right, even if you don't know Chinese, or I'm not even sure if that's Arabic, it might be Arabic or it might be something else. I think it's probably Arabic. And then we have, this is near and dear to my heart. It's my ancestral language, I think. It's Gujarati. Can anybody confirm?
Yeah, that's Gujarati.
Yeah. And we have Japanese, and then I think this is Armenian. And I should know what this is probably the easiest one, but I'm not sure I know what it is. Russian. No.
Hungarian.
Hungarian. Yeah. Yeah, it can't be Russian because it's not.
It's like,
Okay, so anyway, these are some examples, and these are a list of the possible output classes when we do this experiment. The observation is that a human can distinguish these without necessarily being able to speak these, right? And we can do it from a distance. And so we're not recognizing characters. When I say this is Japanese, I'm not recognizing any single character here when I say that. Right? How can we do that without speaking the language? Well, maybe there's some, low-level vision, high-level vision, some vision thing going on, right?
Oh, well, because we live in Silicon Valley, we have some...
That could be, I think...
we have seen enough,
Yeah.
We ride the bus.
Okay, so let's train some convolutional neural net type thing, and do sliding image patches and train some system, and we get very good results. Right. So the idea is that this can be now done as a first pass to handle some of those early examples I showed where you might have mixed scripts within a page, certainly at the block level, paragraph level, column level. But even within a paragraph, you can imagine at least being able to give some hints to your underlying OCR engine that you can prune away much of the hypothesis space, because even though I don't know if this is traditional Chinese or simplified Chinese, at least I know it's not English. And so you can start to feed useful information to your OCR engine. Okay, so these are some of the scripts we handle. Apologize for the formatting, it spilled somehow. But, okay, when my colleague Dimitri presents a slide, he asks the audience if anybody in the audience feels that they could correctly name every single script here.
No.
Okay. Okay, so here's an indication. So countries have official languages, and so one early metric for us was to try to cover all of the official languages in the world, and that turned out not to be that hard. And so we don't cover all of the world, but maybe that's okay.
It's not a country.
It's not a country. It's a region.
It's only in the present time.
It could be eventually inhabited by people who end up speaking some language.
It is inhabited.
Well, no,
But it doesn't have any native language.
Oh. Is it permanently inhabited by people who, are they just on bases, or do they actually?
Yes, maybe pictures on.
Are there people who are like born there and go to school there and all that?
Argentinians, for nationalist military reasons.
Ah, okay. They claim it, or so Spanish is the official. We cover it.
Well, it's of one peninsula.
Oh.
Wait for global warming to kick in.
Okay, so I'm going to make some brief comments now because I'm really running towards the end, I guess. Radha, how strict is that? Actually, let me not ask that. That's a bad question to ask. It's an impolite question. You guys want to go home, so I'll be quick. Okay, so Unicode of all things, which happened way after most of the investment was made in OCR by the big forces that made investments. Unicode is actually very enabling for OCR because it allows you to define the problem. Especially for things like Japanese and Chinese and Indic languages, people were trying to do OCR, but they had nowhere to put it. Nobody agreed on what the representation would be. And that sounds, from a pattern recognition or signal processing point of view, that may not sound like a big deal. But looking back on it, I think that was huge. I think that was a huge impediment for not having an agreed upon goal. There's also, I think, with Unicode, there's a lot of duality and ability to reuse some of the expertise and idea. One that we're taking advantage of is our ability to train on synthetic data, thanks to advances in typesetting, the availability of large amounts of digital text in all languages. Document image decoding, I mentioned earlier, the PostScript model, trying to invert the PostScript model. They also took advantage of this duality, but it was a little bit before Unicode was really fully available, and the DID stuff was pretty much English only. And another place duality turns up is in the noisy channel model, right? At least conceptually.
Well, weren't you at Park, and they had an internal system for doing that?
We had
starting about 1980.
Yeah, we did have some internals. And that's a good observation in general about Park, right? A lot of the nice stuff that happened in Park was because there was pockets of expertise and things that didn't exist anywhere else in the world. So a lot of the progress I think happened because of that. Getting Unicode sorted out and also the typesetting really forced a good understanding of some of the internationalization and other issues, bidirectional and other issues that otherwise it would have been just too much for a small group at Google, or even a large group probably, to figure out on its own. So we can leverage a lot of that stuff. And so I claim, you know, I could be wrong about this, and looking at it, it looks a little bit too strong to say. But maybe when most of the investment was made in OCR, it could not possibly have been solved back then. And now maybe there's less incentive for investments to be made because there's not a lot of money to be made by selling Khmer OCR systems. So anyway, these are, by the way, I'm in this section of my talk where these are just reflections and observations, and I don't claim to be right about any of this stuff. Okay, this is kind of interesting. So they're changing styles and orthographies. So does anybody recognize this language?
No.
Louder?
No.
I think it's Malayalam. Yeah. And depending on how old you are, you might prefer one or the other. And the reason is because there was a change
Depending
in
on how old you are, you might be able to tell the difference.
That too, yes. But you can see it actually if you look here at this character, and you can see that there's a kind of a making explicit of that modification, and you'll see that sort of thing all through. So this is the reformed orthography, about, I don't know, 40 or 50 years ago. I'm not sure when it really came into being. And this is the traditional orthography. So one question is, well, you're building an OCR system, so can you really just say Malayalam, right? Is there one Malayalam script and one Malayalam language from the OCR point of view, or do you really have to decide, you know, am I looking to the future and the young people, or am I going to handle the cultural works that are in other?
So,
sorry,
in this case, can you depend on it being one or the other, or does it get mixed like Japanese does?
Oh, I think the mixing is rare. You could have a book about the orthography reform that would give examples of multiple words.
But typically in Japanese you have a mix.
Yeah, so I think in general we want to handle mixes, and so my answer to that question actually is we want to assume that there's always going to be a mix.
How does Unicode differentiate this?
Good question. I don't know.
Wouldn't that be the source of truth?
Oh, well, Unicode, I think in their charter, I could be wrong, claims to be interested in modern languages and what's currently used. So they might have defined the problem away by saying, well, the orthography reform happened years ago. I mean, Russian had the same thing. There's pre-revolution Russian, imperial Russian, right? And there's some characters that only occur in pre-revolution Russian. And so that's another example of an orthography change that we actually handle very well in our system. And in general, we're good at this kind of stuff because we can be data-driven and we don't make strong assumptions. We cover 200 languages, and that's more than most OCR systems. Here's Fraktur, and by the way, Fraktur isn't just German. It's also, you know, Finnish and other, probably Hungarian and other languages were written in Fraktur. And here's something. This isn't machine printed. This is a manuscript, but it's a similar issue, right? You have archaic characters.
And they're different.
Yeah, and they have slight variation. You know, the scribes or the amanuenses or whatever they're called might have varied from place to place or even within a manuscript. Okay, so is this my last? Oh, that's almost my last slide. I'm very close to the end. So I thought I'd be provocative. I'm talking to signal processing people. And when I dabbled in signal processing in grad school, it was all about what was respected, what people kind of looked up to. Was if you had a theorem and proof and a couple of lemmas leading up to it, then wow, that's cool. You know, you get published, you get respected, right? You know, rigorous. I just threw a bunch of stuff like Gabor, right? Gabor is jointly minimizing spatial moments in the frequency and space domain, and right? But wait a minute, aren't those continuous and we're going to discretize it and then it's no longer optimal? Oh, well, let's just not worry about that. It's optimal. Principled, you know, equal ripple, Parks-McClellan-Remez exchange algorithm, right? These are things that we grew up with in signal processing, right? Equal ripple, you know, specify the stop band with this much importance and all that, right? But wait a minute, when you try to do that and you're doing image processing, you're going to see ringing if you try to like design an anti-aliasing filter that's a good brick wall filter from a theoretical point of view. All of a sudden, we're very sensitive to that, right? So maybe you want a single drop off, a single side lobe that goes below zero, but then flattens out. You know, there's perceptual phenomenon that gets in the way of theory, but still we write papers about optimal and principled. Okay, well, what's the alternative? Well, back then there was a great virtue in doing that. I think there's still, obviously, I'm being a little provocative on purpose here. I mean, you still need to have theory, I think, and you have to have understanding. You have to iterate between theory and experimentation. But I claim that theory is much less important, at least to me. You know, I haven't used the residue theorem in a long time. Does anybody use the residue theorem today? So I think, signal processing has evolved, right? Does anybody design Butterworth filters? Okay. Okay, anyway, but so the contrast that I'm trying to make here is that if you put your energy into good eval data, rich training data, in a robust regime of testing and evaluation, ideally on live systems that are end-to-end, that are real systems that are serving real needs, and have the instrumentation in place to be able to get feedback, then going back to this claim that I made, it doesn't matter how many hidden layers we have in our neural net. It doesn't matter what our topology is. The reason it doesn't matter is because we have a good way of always improving. We'll never go backwards because we've invested in our data. We've invested in our evaluation frameworks and metrics. And so we can use this stuff if it works, if it's good. If we get some fresh PhD who comes in who wants to do L1 regularization or some kernel method or some embedding that has some name attached to it that I've never heard of, great, let's do it. I have no religion about this. Let's do it, but then let's prove it. And we'll check it in and we'll productionize it and we'll flip the switch and we'll turn it on when it's better. Right? So that's my epiphany over the last few years. Okay, what about academia versus industry? I think each has its strengths. They have evolving roles. Somebody once told me that they think all the interesting research in computer vision is happening in industry, not in academia. I think that's too strong. I think there's a great potential for collaboration, but let me leave further discussion about that to the questions. And I think there's interesting ways that we might collaborate. I think it's more problematic between two different two different companies. That might be more difficult. But again, this is stuff that I don't know much about. Okay, can OCR finally be a solved problem? So I want it to be. And what do I think that would look like? Well, then it should be available to anyone, anywhere, free of charge. That would be nice. Right? So in some sense, if you want to translate something, it's more of a solved problem than it used to be. What do you do if you want to translate something from one language to another? Just anybody?
Google Glasses.
Google Translate.
Yeah, you can go somewhere. You can just do it, right? You can go to translate.google.com, cut and paste, and you get something reasonable.
Point word lens at it.
Point word lens at it, right? So it's getting to be kind of solved, right? In a sense. I mean, you don't go off and order some software that only translates Japanese to French, and you have to pay a lot of money for it, and there's a license renewal, and do you run it on one machine, or can you get 5 seats? Or
more importantly, these days, you try a machine effort rather than going off to find a person first.
That's right. That's even a higher level point. That's an even more important point, that it is plausible now to have machines do this, whereas you wouldn't think of doing that even 12 or 13 years ago. Okay, ideally you shouldn't have to connect to a network or send your sensitive documents off to some company, no matter how trustworthy and nice that company is. You should not have to do that.
Word length.
Yeah, word length happens on your device. Yep. But now, word length doesn't cover most languages. That's currently the case. Now that may change. My guess would be that we'll see more languages over time, probably. Okay.
But again, all of this is full of 80-20 problems, and word lengths attack the 80%.
Right. Yep. Unless you're in Cambodia, in which case it handled 0%.
Well, if you're in Cambodia, you're in the 20%.
So I have these kinds of discussions all the time at work. I'm actually a believer in all languages should deserve our full respect and equal respect. But then I don't claim that that's...
Well, that's a lovely point of view, but it's not economically driven.
Do I want to be economically driven?
You work for a profit-making company, yes.
But, you know, how much money does Translate make for Google?
Well, and within that domain, how much money does Cambodian make within the realm of Translate?
I think there's a lot of value to having Google be a go-to place for things, even if we're not making money off of anything. In those, I mean, we want to make money off of something, right? I think we're making some money off of advertising. But I don't think everything that we do, I think we can make the world better, and it's in everybody's interest, including Google's. That's my personal point of view. And
that's a lovely fantasy in an immature company.
Okay. You have more gray hair than I do, so I'm not going to...
I used to work for Xerox.
Okay. Were you at Park?
Yeah.
Cool. Okay, let me finish up here. So I also think that, you know, efforts from, like the world's information, there's a lot of cultural heritage that's tied up in regional libraries, in regional newspapers, and I think that would be kind of an interesting next layer of material to make available online, right? It's untapped, it's rich, right? There's plenty of, you know, chat room logs and whatever that is currently available in the digital world, or at least it exists somewhere, who knows. There's plenty of, you know, on Facebook, there's plenty of, you know, LOLs and, you know, likes, right? There's a lot of digital information, but compare that with, you know, somebody's treatise on something that was, or period piece in a newspaper that talks about a certain architecture and how it differs from the previous version of that building, and, you know, that just is hidden from the world now, right? It exists, but it's in some library printed somewhere.
Well, yeah, there's lots and lots of stuff on microfilm to be converted.
Right. So newspapers, exactly. So I don't know if you know that Google had some effort in that area, and that a lot of that data still exists. And in Europe, there's a huge effort now in digitizing newspapers, and a lot of them are in microfiche. So there are lots of challenges there. Our system, by the way, works really well on that. We've tried it already. It works really well.
Well, speaking of Xerox, that was Xerox's ambition at one point. They bought University Microfilms, which was the world's archive of microfilm when they bought it.
Oh, so what happened to it?
I think they gave up. They had to make a profit.
So I think, you know, profit and everything is interesting, but and maybe I'm naive, but if I'm naive, then a lot of my colleagues are also naive, and we're doing it anyway.
You work at Google.
We're doing it. We're making this. We want to make the world better. We want to allow the world to get its full rich heritage in a form that's most useful.
So text is data, data is analytics, and analytics is advertising is money for Google. That's how it works.
Okay, well, so then it's win-win, right? We can make the world better, and it's win-win. I wanted to mention, thanks to Janusz for this slide. This is a product manager slide. This is, you can tell because it's beautiful, right? I had Bayes' rule with this ugly alpha as an exponent, and here we have beauty. So thank you, Janusz. Do you want to say anything about this? I mean.
Yeah, so these are a few examples of Google products in which we have OCR technology. Some of these are apparent, like Google Book Search, where we scan a lot of books and we have to do OCR. But there are some which are not so apparent, like in Google Drive, if you upload some documents, we OCR them so that you can retrieve them later for indexing. This includes images as well. There are Street View cars that go around taking pictures, and we need to OCR the street signs. There are apps on the phone like Google Keep and Translate, which has word lens that lets you do OCR in a very interesting way. That's just a few of the examples. There are many other products which use OCR as an embedded technology.
Thanks. And it is a beautiful slide.
Thank you.
Okay, I think that may be it. Oh no, I don't have my thank you. Let me just say it. Thank you.
So we're running a little late. We probably have about 10 minutes for questions, but before we start, I wanted to give a gift to our speaker. As
wow.
Thank you. Thanks a lot for coming to speak to us. We really appreciate it.
Thank you.
Okay, no problem. It's yours. Don't give it back to me.
Well, I was waiting for the last picture where I'm looking at you.
I know.
Well, it's
so
beautiful.
10 minutes.
Can you do handwriting recognition better than the Apple Newton?
I think the answer is yes.
Okay. How about the non-phonetic languages doing that double OCR trick? Does that work on that too, or tonal languages?
So for CJK, handwriting recognition for device input is very important. And native Chinese writers learn a particular stroke order that knowing in advance, because we have the timing trajectory, is very helpful for recognition. We can do quite well. I don't think we've tried yet internally much in the way of recognizing Chinese in the absence of that stroke information, that time trajectory information. Okay. But we have tried it for other languages, and you take a hit in accuracy, but I mean our goal is to be useful and to be, one metric would be to try to be the best in the world, and I think it would be nice to get there. Yep.
So captures are being used to distinguish man from machine, right?
Yep.
If this becomes really super good, will this defeat the concept of super good?
Well, I think that's captures are an arm race. It's an arms race, right? In the sense that if OCR becomes really good, then the capture designers will do something else that makes it harder. And personally, I know a lot of people are interested in that area, but my interest is actually to make stuff to successfully and accurately OCR material that was made for human consumption to inform them of something useful and interesting. And captchas are not in that field for me. Yep.
So some of these items on the slide beg the questions. So are you working on a single script that can work on any compute engine, or have you looked at any benefits of having customized hardware or systems that might speed up or give you better accuracy?
Right. So
modules?
So as things migrate towards neural nets of one form or another, it's not just OCR that's doing that, it's computer vision, it's a lot of different fields. I think we'll probably see hardware manufacturers stepping up and making chips or subsystems that do the computations that are most needed in those areas. So if we continue to go in the direction of neural nets and recursive neural nets, deep neural nets, then probably we'll leverage those same advances.
For real-time OCR, what are the special techniques that you use so that it can be done? Like the example that you used, to take a photo and then get the translation right away.
Right, so there's two levels to kind of real time. There's the real time, which is actually happening at the rate of multiple frames per second, which is word lens. And then there's kind of OCR that could happen very quickly, but not at multiple times per second for the whole frame. Word lens, I don't know what's public about. We sit in the same building as those people, and so we sometimes talk. And what they do is incredible, and they know stuff about doing stuff quickly that I can only worship and dream about. I don't know how much is public for me to actually say even to summarize what I know in more detail than that, so I'd rather not. But you can probably, if you do a web search on it, Bing or or Google, right? Then you'll probably find the answer. Yep.
Are you doing any voice recognition with your work, or is that disjoint?
We talk to those teams about pieces like language models and decoders and things like that. Porting stuff on device to work on ARM. We're in contact with each other, and there are synergies that can benefit these projects.
Being able to talk to customer support.
Customer support?
Yeah.
Well, that would be great. Does Google have customer support?
Not that I found.
I've never had.
They
do. Okay.
We're buying things.
Okay.
Google doesn't even have a phone number. Try calling yourself on the phone and see how far you get.
So maybe we'll make this maybe one more question, and then I'm sure Ashok would be around for a few more minutes afterwards.
Yeah, definitely.
So at a translation level, even at a sentence level, if you try to translate a given language into a different language, there are a lot of mistakes.
Yep.
If you know both languages, then is that the next step, or is it something that's entirely outside of your?
So let me make sure I understood the question. So for the translation,
even if you try to translate either say a Chinese sentence into English or English into say Russian,
right.
There are a lot of mistakes.
There are, yeah.
That you can find in terms of perhaps even syntax sometimes.
Sure, yeah.
So would that be considered the next step, or is it something that is handled entirely by some other?
So actually, I'm no longer on the Translate project, so I'll interpret that, if you don't mind, as an OCR. There's an equivalent OCR question. So I mentioned that we're working on isolated text lines, but one thing I didn't mention is that there is value and benefit in propagating information that is aggregated from larger units than a sentence to take advantage of that information when OCRing a text line. So, for example, the typeface is probably the same on the page, right, from line to line. The topic may indicate that you want to use a certain type of language model, for example. So we're aware of the need for doing that. Let me try to actually go back to the translate point. I think the same is true for translate. Typically, translate, though, does formulate the problem in terms of larger units of text. Now, there are phrases, right? It's a statistical phrase-based translation that we've written about in papers. And those phrases are on the orders of, a few words or maybe slightly longer for non-compositional compounds and maybe some idiomatic things that are special cases or stuff like that. But I think if the thrust of the question is, does working in small units create the potential for errors that would be mitigated by working in longer units in more context? I think the answer is clearly yes.
Okay, so let's thank our speaker again.